Auth bugs pay the most in bot bounty. Account takeovers, token theft, session hijacks, 6 figures on a single report, sometimes more. And most hunters never touch them. Not because they can't, because they don't really understand Auth. They see state, code challenge, direct URI in their proxy, and they scroll past it. They open a JWT, they squint at the 3 bars and they close it. I don't blame them. Every guide opens with a textbook definition. RFC this, specification that. By the time you finish, you still can't tell me why redirect URI exists. You still can't tell me what it actually protects. So forget all of that. In this video, I will show you Auth, the way the developer who built it sees it, why each piece exists, why it protects against, what assumptions is quietly making about you. By the end, you will open any Auth flow on any target and instantly see the seams, the places where the developer trusted something they shouldn't have, the places where the bug lives. I'm not breaking any of these flows today. That's a video of its own, coming later, but you can't break what you don't understand, and we start here. One quick thing before we get into it. In a recent video, I asked you a question: should the next big deep dive be Auth? Look at the responses. You asked for this video, and here it is. So this is AmrSec. Go get your coffee ready and let's dive in.
The channel has enough content.
As this is like look download that in podcast. Every system on the internet has to answer 2 questions about every single request that comes in. The first one is, who are you? That's authentication. The login flow, the password check, the session cookie, the token in your header. Anything that proves you are not a stranger walking on the street. The second one is, what are you allowed to do? That's authorization. The permission check, the role check, the ownership check, the scope enforcement. The thing that decides whether this specific user can perform this specific action on this specific resource. Authentication is identity. Authorization is permission. 2 completely separate decisions. And here is the thing nobody points out clearly enough. Most companies get the first one right and the second one wrong. Authentication is a solved problem. Use a library, plug in a session manager, hash your passwords, done. The patterns are well known and the tooling is mature. Authorization is a custom code. Every endpoint has its own logic. Every action has its own check. Every resource has its own ownership model. Nothing is reusable. Everything has to be implemented over and over again by hand on every single route. That's why the bugs live there. Think about every broken access control bug you have ever read in a write-up. An IDOR where you swap a user ID and pull someone else's data. The server authenticated you correctly. It knew exactly who you were. It just didn't check whether that resource you were touching belonged to you. Authentication paused, authorization failed. A privilege escalation where a regular user calls an admin endpoint. The server authenticated you correctly. It knew you were logged in. It just didn't check that you had the admin role. Authentication paused, authorization failed. An OAuth scope bypass where a token with read email is used to write a calendar. The server authenticated the token correctly. It verified the signature. It just didn't enforce what the token was actually allowed to do. So again, authentication paused and authorization failed. The same pattern every time. The bug is never in the login. The bug is in the gap between knowing who you are and knowing what you can do. Now here is the part most people skip. Why is any of this hard to begin with? HTTP is stateless. That's the rule. HTTP was designed in 1991 as a protocol for serving documents. You ask for a page, the server gives you a page. The connection closes and the server immediately forgets you exist. The next request is a fresh start. No memory, no history, no identity. For documents, that was fine. For application, it isn't. If the server forgets you between requests, how does it know who's making the second one? Every authentication mechanism you have ever seen existed to solve that exact problem. The session cookie, the barrier tokens, the JWT and authorization header, the signed assertion in a SAML response, every one of them is the same trick. The client carries proof of identity on every single request and the server uses that proof to remember who you are. That's it. That's all Auth is. A long chain of workaround because the underlying protocol forgets you the moment you finish your request. And every workaround has assumptions backed into it. Every assumption is a place where a developer trusted something they shouldn't have. Every trust gap is where you and I get paid. So here is the frame I want you to carry through the rest of this video. For every request you intercept on every target, ask two questions. How does the server know who I am here? And how does the server know I am allowed to do this? If you can answer both with confidence, the surface is solid. If either answer is the server is trusting the client, you already found a bug. Authentication is identity. Authorization is permission. The gap between them is where you live. Let's start with the simplest authentication mechanism on the internet, a username and a password. When you submit a login form, your browser sends a post request with your credentials. The server has to decide two things: is this username real and does the password match? So how does the server know if the password matches? Here is the thing: the server doesn't store your password, not directly. If it did, every database leak would be claustrophobic. Your password would be sitting in a CSV file somewhere, plain text, alongside 10 million other users. So instead, the server stores a hash of your password. A hash is a one-way function, easy to compute forward, impossible to reverse. You give it a string, it gives you a fixed length value back. The same input is always produces the same output, but going the other way from hash to original string is computationally infeasible. Modern password hashing has two properties that matter for hunters. First, it's slow on purpose, a configurable work factor. Every password verification takes 100 milliseconds, maybe more. That's nothing for real user logging in. But for an attacker who got their hands on a leaked hash database, it is the difference between cracking everything in a day and cracking nothing in a decade. Second, it's salted. A salt is a random unique value added to your password before hashing. So even if two users have the same password, for example, password 12345, their hashes are completely different. This calls rainbow tables. Attackers can't pre-compute a dictionary of hashes ahead of time because they don't know the salt until they have the leak. The modern algorithms you will see by name are bcrypt, scrypt, and Ergon2. If those appear in a write-up, the company did the right thing. If you see MD5 or SHA-1 without salt, GPU farms crack the entire database in a weekend. That's all you need to know about hashing for now. The takeaways is just this: the server never has your password. It has a stretched, salted hash of it. When you submit your password, the server hashes what you sent with the stored salt and compares the two hashes. If they match, you are authenticated. But authentication is only the first request. What happens on the second one? And this is where sessions come in. Remember, HTTP is stateless. The server forgets you the moment your login request finishes. If you don't carry something with you, your next request will look like a fresh stranger walking off the street. So the server creates a session. A session is a record on the server side. It says user with ID 12345 logged in at this time. Here is their permission. Here is their last activity. The session has a unique identifier, a random string, long enough that nobody can guess it. That string is called the session ID. The server takes that session ID and sends it back to your browser as cookie. The browser stores it, and from that moment on, every single request your browser makes to that domain automatically includes the cookie. The server reads the cookie, looks up the session in its own store, and remembers who you are. Let me show you exactly what this looks like in real traffic. Alright, so here I have login form and this browser is proxied to my Kaido. So here what I'm gonna do is basically write my credentials, the username and the password, okay? And once I hit sign in, you will see I am authenticated. Now I will go back to my Kaido here and you will see we have here two requests. First request is post to /login endpoint. And if I click on it and show to you right here, you will see we have here the username and the password in the body. Nothing complicated. Now if I go back to the response, you will see here that it's basically redirecting me to /dashboard, but check this out here. We have set-cookie and here we have the session ID. So basically the server just handed my browser a session ID and this random string is my identity now. In the next request, we have get request to the dashboard, but there is something different here. In the request, we have cookie and in the cookie, we have session ID. If I get back to the request before, for it and get this copy and go to the next request and search here with it, you will see here that it exactly matches, which is my session ID. So basically same cookie written on every single request, subsequent request automatically. The server reads this on every hit and looks up who I am. The cookie is me to the server. If anyone steals this value, they are me. No password needed. They paste this string into a cookie header and the server treats them like they are sitting in my chair. The last point matters more than people realize. The session cookie is not a key to unlock your account. The session cookie is your account. To the server, you are not a user. You are a string of bytes in a cookie header. You have the string and you are now the user, which is exactly why the rest of this matters. If the cookie is everything, the cookie has to be protected, and the protection are built into the cookie itself. As flags, there are dozens of cookie attributes defined in the spec. For a hunter, 3 matters more than all the other combined. Number 1, HTTP only. When a cookie has HTTP only flag, JavaScript can't read it. Documented cookie pretends it doesn't exist. The only thing that handles the cookie is the browser itself, sending it on requests automatically. Why does this matter? Because XSS exists. If an attacker can run JavaScript in your page, the first thing they want is your session cookie. Without HTTP only, the attacker writes one line, document.cookie, sends the result to their server, and now they have your session. With HTTP only, the exact attack just doesn't work. The XSS still runs, but the cookie is invisible to it. If you see a session cookie without HTTP only in a live target, that's a finding by itself, and it turns every reflected XSS on that domain into a full account takeover chain. Number 2, secure. When a cookie has the secure flag, the browser only sends it over HTTPS. Plain HTTP requests gets no cookies at all. So again, why does this matter? Because plain HTTP is readable on the wire. A coffee shop attacker on the same network can sniff packets and pull out cookies. With secure, even if the user accidentally load http example.com/something, the cookie doesn't go to that request. It stays on the browser. If you see a session cookie without secure on an HTTPS site, that's a clean finding, low most of the times, but it is reliable. Number 3, same site. This is the most misunderstood of the 3. Same site controls when the browser sends the cookie on cross-site requests. There are 3 values: strict, lax, and none. Strict means the cookie is never sent if the request was initiated from a different site. Most lockdown options. It also breaks things like clicking a link from a different domain and arriving already logged in. Lax means the cookie is sent on top-level navigations, like clicking a link, but not on sub-resource request, like an image on a different site firing a GET to your target. Lax is the modern default. If a cookie is set without an explicit same-site attribute, the browser treats it as lax. This has started rolling out in Chrome 80 back in early 2020. None means that the cookie is sent on every cross-site request, regardless of how the request was initiated. This is the old behavior. If you set same site to equal none, you have to also set secure, or modern browsers will reject the cookie entirely. Why does this matter? CSRF, cross-site request forgery, the classic attack where you trick a logged-in user into visiting your malicious site and your site fires a request to the target. Before same site, that request automatically carried the user's session cookie and the target server treats it as legitimate. With the same site, lax or strict, the cookie doesn't go along for the ride, and the CSRF dies on arrival. If you see a session cookie with same site equal none on a site that actually doesn't need cross-site cookie sending, that's a CSRF service worth investigating. Let me show you what these flags looks like in a real browser. So here, as you can see, I'm still authenticated. So if I right click here, go to inspect and go to storage, you will see here that on the left sidebar we have cookies and my URL is selected, and here is the cookie name and value and the 3 flags I just walked you through right here in the table. That the cookie is HTTP only, which is true, that means it is checked. Secure as well, so it is true, and the same site is lax, and the basics are in place. That's what a responsibly configured session cookie looks like. That's the entire classic model. Password get hashed, server stores the hash, server logs in, the server creates a session, server sends a session ID as a cookie. Cookie travels on every future request. Cookie is protected by HTTP only, secure, and SAMS high. When everything works, that's a clean authentication system. It has been the foundation of web applications for 30 years. Now, where does this break? The session ID has to be unguessable. If it's predictable, anyone can guess yours. If it's based on sequential counter, an attacker increments and walks the entire user table. Modern frameworks use cryptographically random IDs, so this is mostly solved. But you will be surprised how many internal apps and legacy systems still get this wrong. The session has to be invalidated on logout. Some apps just clear the cookie from your browser and call it done. The server-side session record is still alive, which means if anyone stole your cookie before you logged out, they still have a valid session after you logged out. Real logout should destroy the session on the server, not just delete it from the browser. The session has to expire. Sessions that never time out are sessions that never gets cleaned up. A leaked cookie from 2 years ago shouldn't still log you in. Real sessions have a TTL. Real sessions stores enforce it, and the cookie has to carry the right flags. Missing HTTP only turns every XSS into an account takeover. Missing secure turns every accidental HTTP request into a credential leak. Missing same site turns the site into a CSRF playground. We will get into how attackers actually exploit each one of these gaps in the future video. For now, hold this in your head. The session ID is the account. Every flag on it is a wall around it. Every wall that's missing is a path to ownership. Sessions have a problem. Every request hits the database. Browser sends the cookie. Server pulls the session ID. Server looks up the session in the store. Server finds the user. Server processes the request. For a small app, that's nothing. For an app handling a billion requests a day, that's a billion database lookup just to figure out who's sending each request before any real work even happened. And then microservices showed up. Now you have got 10 different backend services. Each one needs to know who you are, and they all are asking the same session store. The session store becomes a bottleneck, then a single point of failure. So engineers asked a question: what if the proof of identity carried itself? What if the cookie was the entire session, not just an ID pointing to one? And that's JWT, JSON Web Token, the most popular implementation of a stateless authentication on the modern web. The idea is simple. And instead of the server keeping a session record and handling you a pointer to it, the server packages all the relevant information about you into a token, signs it cryptographically, and gives you the token directly. From that point on, every time you send the token back, the server reads it, checks the signature, and trusts all the content of it. No lookup, no state, the token is the session. And that's the pitch. It's a real win for scaling, but it opens an entirely new category of bugs that doesn't exist in the classic session model, because now the token itself has to be tamper-proof, and a lot of servers gets that wrong. Let me show you what a JWT actually looks like. Alright, so here I have the login. If I write my credential here and login, as you can see, it logged me in. Now I will just go to Kaido here and check everything. So basically the first request was post request to /login. It had my data in JSON body here, and the server returned back a JSON token, and this is JWT token. After this, you will see that the get/API/me used this token. So what I'm gonna do is I will copy this token right here, and I will go to JWT Analyzer, go to JWT Editor, and paste it here. So basically, this is real JWT, pulled live from the app I just looked into. Looks like a random gibberish, but it isn't. It is 3 pieces separated by dots. So here, this is the first piece, second piece, and the third piece. First piece is the header, second piece is the payload, and the third piece is the signature. Each one is base64 encoded. The moment they decode, the whole thing becomes plain JSON you can read. So here, for example, example, we have the header. The header tells you what algorithm was used to sign this token. In this case, we have HS256 here. We will get to what that means in a second. And after this here, we have the payload. And the payload is the actual claims. Who is this token for? When it was issued. And when it expires, what they are allowed to do. This is the part that the app cares about. As you can see here, we have the sub, we have the name, which is my name, we have the email, again my email, and we have the role here and the expiration of the token. And before I keep going, look at this carefully. This isn't encrypted, it is base 64, which means anyone holding this token can read every claim inside it. Do not ever put any secrets in the JWT payload. People do it all the time. But here we have the header and the payload, but there is no signature. And as I told you, the last part is the signature of the token. So basically, signature is the only thing keeping the rest of this token honest. Without it, anyone could forget token. And with it, the server can prove the token was issued by them and that nobody has tampered with it in transit. So a JWT is three things: a header that says how it's signed, a payload that says what it carries, and a signature that proves both of the above hasn't been touched. But here is where it gets interesting for hunters. The payload is base 64, not encrypted. Anyone who intercepts the token can read what's inside. So the first thing you do when you find a JWT on a target is decode it and look at the claims. Half the time, you find more information than the app should be exposing. Internal user IDs, permission flags that hints at admin panels, source of truth identifiers from the backend system, all of it sitting in a plain text base 64 wrap in a token the app handled you directly. The other thing, the payload tells you what the app trusts. Let me show you what I mean. So here, what I'm gonna do is change role from user to be admin. So here I will just remove user and make it admin. And again, it didn't update it yet, but check this out. When I click update token from JSON, you will see it updated. I just changed it to one claim and the encoded token rebuilt itself, new base 64. And look at this part. The signature is invalid because the signature is computed over the header and the payload combined. The moment I change it a single character, the signature is no longer matches what the server signed. And this is the entire security model. If I tamper, the signature break. If the server actually checks the signature, my tampered token gets rejected and game over. But if the server actually checks the signature, and we will come back to that later. The last point is the whole game. If the server verifies the signature correctly, JWTs are solid. The math is sound. Cryptographic signatures are not breakable in any practical sense. If the server doesn't verify properly, the entire system collapses. The token is just a base 64 string the attacker can rewrite however they want. And we will get into exactly how that goes wrong in future video. For now, you need to know the two main ways JWTs are signed, because the difference between them creates an entire attack surface on its own. The first one is HS256, HMAC with SHA-256. This is symmetric. There is a single secret key. The server uses that one secret key to sign the token, and the server uses the same secret to verify it. Whoever has the secret can both create new tokens and validate existing ones. This works fine when there is only one server. The secret lives on that server. Signing and verifying both happen in the same place. Life is simple. The risk is that if the secret ever leaks, an attacker can mint their own tokens with whatever claims they want. So secret strength matters. A short or weak HS256 secret can be brute forced offline once you have any valid token. That's a real bug class. The second one is RS256, RSA with SHA-256. This is asymmetric. There are two keys, a private key which only the server has, and a public key which the server is happy to give out to anyone who asks. The server signs the token with the private key. Anyone with the public key can verify those signatures, but the public key cannot be used to create new tokens, only to verify them. This is why most large large-scale systems use RS-256 instead of HS-256. The OAuth server holds the private key. Every other service in this system just needs the public key to verify tokens. The public key is meant to be public. There is usually an endpoint at something like /.wellknown/gwks.json that hands it out openly by design. So when you intercept a JWT on a target, look at the ALG in the header, the algorithm. If you see HS-256, the server is doing symmetric signing and there is a single shared secret living somewhere on the backend. If you see RS-256, the server is using a public-private key pair and the public key is likely sitting on the JWKS endpoint you can fetch yourself. That distinction matters a lot because the validation logic for each one looks different and the bugs in each one looks different too. We will come back to that later. For now, the last thing is to understand what the server is supposed to do when a JWT comes in. Step 1. Decode the header, look at the algorithm field, ALG. Step 2. Verify the signature using the correct key. For H256, that means the server's shared secret. For RS256, that means the public key for the issuer that minted this token. Step 3. Check the expiration. The EXP claim is a timestamp. If it's in the past, rejects the token, no matter how perfect the signature is. Step 4. Check the other claims that matter. The ISS claim should match the issuer that server expected. The AUD claim should match this server. So a token meant for one service can't be replayed against another. The MBF claim, if present, says the token isn't valid yet. Step 5. Trust the rest of the payload. Once the signature is valid and the standard claims is checked out, the server treats the rest of the payload as ground of truth. Whatever rule, scopes, or permissions in there, that's who the user is. And that last step is the whole reason JWTs are so powerful and the whole reason why JWTs are so dangerous. If the validation chain works, the server can authoritatively trust the payload. No DB lookup, no session store, nothing, just math. If the validation chain has a single weak link, the server is now trusting whatever the attacker puts inside. Here is the assumption every JWT implementation makes. The server trusts the algorithm the client tells it to use. Read that again. The algorithm is in the header. The header is part of the token. The token comes from the client, which means the algorithm the server is verifying with is technically a value the client controls. That's the entire back class right there. We will dig into exactly how that gets exploited in a future video. The most famous version of it is algorithm none, where an old library accepted a token whose header declares an algorithm is none and skips signature verification entirely. There is another version called RS256 to HS256 confusion, where the server takes the public key it was supposed to verify with and uses it as an HMAC secret instead. And there is a whole family of header field abuse around key ID, JKU, and X5U, where the attacker tricks the server into fetching the wrong key. None of those are exploits we are running today. They are the room upstairs in the house, and we are still building the foundation. For now, hold this in your head. A JWT is 3 base 64 strings joined by dots. The payload is readable by anyone. The signature is the only thing protecting it, and the algorithm used to verify the signature is declared by the same untrusted party that sent the token in. That's the C. Sessions and JWTs both solve the same problem. How does a single app remembers who you are between requests? OAuth solves something different. How do two apps work together on your behalf without you handling one of them, the keys to the other? Let's say you use Calendly. Calendly needs access to your Google Calendar so it can check your availability and book meetings. How does Calendly actually do that? Before OAuth, the answer was uncomfortable. You gave Calendly your Google password. Calendly stored it on their servers. When they needed to talk to your calendars, they logged in as you using your credentials. This was the standard pattern across the entire internet for years. It was so common. It had a name, the password, and the pattern. Think about what that meant. You handed your master credentials to a third party. Once they had your password, they could read your emails, change your password, take over your account. You couldn't revoke their access without changing your your password, which would break every other app and device you used Google with. And if Calendly ever got breached, your Google password was sitting in their database, plain target for whoever broke in. So in 2010, a working group sat down and built a protocol to fix this. The whole point was to answer one question: how do you give Calendly access to your Google Calendar without giving them your Google password? That protocol is OAuth 2.0. OAuth lets you delegate a specific capability without delegating your identity. Calendly gets the ability to read your calendar, not your email, not your account, just calendar read access, scoped down to exactly what they need that you can revoke anytime with one click from your Google account settings. That's the entire point: delegated authorization without credential sharing. And before we go any further, I have to clear up single biggest misunderstanding people have about this protocol. OAuth is not an authentication protocol. I know you see sign in with Google everywhere and you assume that button is OAuth. It's not. It's OAuth plus another layer called OIDC. We will get to OIDC later. For now, just hold this distinction. OAuth answers what is this app allowed to do with my data. It doesn't answer who is this user. Those are different questions. The reason people conflate them is that login flows often piggyback on OAuth, but OAuth itself doesn't carry identity. It carries permissions. This confusion causes real bugs in production. Apps that treat OAuth as authentication can be tricked because the protocol was never designed to tell the app who the user is. We will come back to that later. For now, let's look at how OAuth actually works. Every OAuth flow has 4 rules. Memorize these. Every bug you will ever find in this space lives between 2 of these rules. Rule 1: the resource owner. That's you, the user, the person who owns the data being protected. In our example, you are the resource owner because Google Calendar is your calendar. Rule 2: the client, the application that wants access. In our example, it is Calendly. In general, any app that says connect your Google account or sign in with GitHub is acting as client. Rule 3: the authorization server, the entity that knows the user, authenticates them, and issue tokens. In our example, Google. More specifically, accounts.google.com, the outside of the platform you are delegating from. Rule 4: the resource server, the API that actually holds the protected data and enforces access on it. In our example, googleapis.com/calendar, the Google Calendar API. 4 rules: you, the client, the auth server, the resource server. Sometimes the auth server and the resource server are the same company on the same backend, like Google. Sometimes they are 2 completely different systems. The rules stay separate even when they happen to live on the same machine, because the trust relationship between them is where some of the nastiest OAuth bugs live. Okay, now let's talk about token. After an OAuth flow completes, the client walks away with 2 things. The first one is the access token. This is the thing you actually use to call the API. Every time Calendly wants to check your calendar, it sends a request to the Google Calendar API with the access token in the authorization header. Prefix it with the word bearer, as in I'm bearing this token, accept me on its strings. The server checks the token, sees that it is valid and has the right scope, and serves the data. Access tokens are short-lived, usually minutes to an hour. The reason is simple. If the token leaks, you want the damage window to be small. A token that's only valid for 15 minutes is much less dangerous than a token that's valid for 6 months. The second token is the refresh token. This one is long-lived, sometimes days, sometimes months, sometimes until the user explicitly revokes it. You never use a refresh token to call the API. The resource server doesn't even understand the refresh tokens. The refresh token has exactly one job. When your access token expires, you send the refresh token to the authorization server's token endpoint, and the server hands you a fresh access token. The user doesn't see anything. No new login, no pop-up. The client just silently rotates the access access token in the background, and life continues. That's why the system uses 2 tokens instead of 1. You get the security of short-lived access tokens, and you get the user experience of long-lived sessions, both at once. But there is a problem with the design that you have to understand. The refresh token is now the long-lived secret. If an attacker steals it, they can keep generating fresh access tokens for as long as the refresh token is valid, which might be months. That's why modern OAuth uses something called refresh token rotation. Here is how it works. Every time the client uses a refresh token to get a new access token, the authorization server doesn't just hand back a new access token. It also hands back a brand new refresh token and immediately invalidates the old one. So the refresh token is a single use. The moment you redeem it, it dies and you get a fresh one in its place. Now imagine the attacker steals a refresh token. They use it. They got a fresh access token and a fresh refresh token. The old one is now dead. They have a working refresh token indefinitely. Then the real user's app tries to refresh the refresh token. The original one is also dead because the attacker already used it. So when they hit the token endpoint, the server sees a refresh token that has been already used. That's the signal. Reuse of a single-use token is the fingerprint of theft. The server can't tell which side is the attacker and which side is the real user. So the server does the same thing. It revokes the entire token family. Every token descended from that original authorization is now dead. The user has to log in again. The attacker is also kicked out. The damage stops there. That's reuse detection. That's why refresh token rotation is mandatory in OAuth 2.1 for public clients like mobile apps and single app applications. Without rotation, a stolen refresh token is a multi-month backdoor. With rotation, the moment theft happens, the server notices and shuts everything down. If you see refresh tokens that don't rotate, that's worth investigating. If you see refresh tokens that have rotation but the server doesn't actually detect reuse, that's even bigger issue. Both are reportable, both are real findings in real bug bounty programs. Last piece, scopes. A scope is a string that says this access is allowed to do this specific thing. When Calendly asks Google for permission, it doesn't just ask for access to your account, it asks for a specific scope. Maybe calendar read if it only wants to see your availability. Maybe calendar read, calendar write if it also needs to create events for the meeting it books. You see scopes on the consent screen. This is the page that says Calendly wants access to read your calendar events, create events on your calendar. Every line of that consent screen maps to a scope being requested. When the user approves, the token issued is bound to the exact scope. Calendly gets a token that can read and write the calendar, nothing more. If Calendly tries to use that token to read your email, the resource server is supposed to look at the scope, see that email isn't included, and rejects the request. The phrase supposed to is doing a lot of work in that sentence. Scope enforcement is the resource server's job. The token contains the scope. The resource server has to look at the scope on every single API call and decide whether the request action is allowed. If the resource server skips that check, scopes means nothing. The token becomes a generic. This user gives us some kind of access, but that opens every door. This is the most common OAuth bugs in production. Server-side scopes enforcement is custom logic. Every endpoint has to do it, and just like authorization we mentioned earlier, custom logic on every endpoint is exactly the kind of thing developers forget on the endpoints they didn't think hunters would check. The other thing to know about the scopes is that any check that happens client side is decorative. If the front end shows or hides buttons based on whether your token has a particular scope, that's a UX feature, not a security control. The attacker doesn't use these buttons. The attacker calls the API directly. The only check that matters is the one on the server. So here is the full picture. 4 rules: you, the client, the auth server, the resource server, 2 tokens, a short-lived access token to call the API, and a long-lived refresh token to keep the client logged in silently. Refresh tokens rotate and reuse detection catches thief. Scope describes what the access can do, and the resource server has to enforce them on every single call. And that's OAuth 2.0. 4 rules, 2 tokens, scopes the server has to enforce. The protocol that lets one app act on your behalf in another app's data without your password ever changing hands. Next, you will see the whole flow as real HTTP requests. Now you have got the model: 4 rules, 2 tokens, scopes. Time to see exactly how they all move on the wire. OAuth defines multiple flows, different ways to actually exchange the tokens. We are going to look at all of them in this video, but first we're going to deep dive on one, the Authorization Code Flow. This one matters more than all the others combined. It's one of the most common flows on the modern web. Every major OAuth provider uses it as their default. Google, GitHub, Microsoft, Okta, every sign in with X button you click is firing this exact flow under the hood. It's also where the most bugs live, not because the flow itself is weak, but because there are 6 steps to it, and each step is a place where a developer can get something subtly wrong. Let me walk you through the 6 steps before we look at them in real traffic. Step 1, the redirect. The client wants to start the flow. It builds a URL pointing to the authorization server, and the redirect is the user's browser there. The URL has 5 parameters that matter. First parameter is response underscore type equals code. Tells the server we are using this specific flow, not one of the others. Second parameter is client underscore ID. Identifies which application is asking. Calendly has a client ID registered with Google. So does every other app that integrates. Third parameter is redirect underscore URI. Tells the server where to send the user back when they are done, and it has to match exactly what the client registered ahead of time. Fourth parameter is scope, the permission being requested, calendar read, email read, profile, whatever the app needs. And fifth parameter is state, a random value the client generates and binds to the user's session. We're going to come back to this one. It's the single most important parameter from a security perspective. So the redirect URL ends up looking like a Google URL with all those parameters tagged into the end. The browser follows the redirect and lands on Google. Step 2, the user logs in and approves. At Google, the user sees a login form if they aren't already logged in. They authenticate and then they see the consent screen, the page that says Calendly wants access to your calendar, allow or deny. The entire step happens on Google's domain, not on Calendly's domain. The client never sees the user's Google password. The client never sees the user's Google authentication at all. The whole point is that Calendly never has any visibility into how Google authenticates the user. Calendly just trusts that Google did its job. Step 3, the redirect back with a code. The user clicks allow. Google redirects the browser back to the redirect URI the client supplied in step 1, but this time the URL has 2 extra parameters. Code, a short random string. This is the authorization code. It's not a token, it is one-time short-lived ticket that client can exchange for actual tokens, usually valid for 10 minutes max, usually single use, meaning once it's redeemed, it's dead. And second parameter is state, the same state value that the client sent in step 1. Google equity it back. The client has to verify that this matches what it originally sent. If it doesn't, the request didn't originate from this user's session, so reject it. Step 4, the back channel exchange. This is where the protocol does something a lot of people miss. The post request contains the code, the client ID, the redirect URI again, and a client secret. The client secret is a long random string that only the client's backend knows. It proves to the authorization server that this exchange is happening from the legitimate client, not from someone who happened to intercept the code. Step 5, Google returns the tokens. The response to that post request contains the secret token, the refresh token, the expiry time, and the scopes that were granted. JSON, server to server. The browser never sees any of this. Step 6, the client calls the resource server. Calendly now has an access token. It puts it in the authorization header with the period prefix, and it calls the Google Calendar API. The API checks the token, verifies the scope, returns the data, and now Calendly gets your calendar events. That's the full flow. 6 steps, 2 redirects, 1 backend channel exchange, and 1 API call. Now, let me show you exactly what each one of those looks like in real traffic. Right, so here what I'm gonna do is basically logging in normally without any problem, and once I'm logged in I will get back to my Kaido here, and check this out. We have the post request to /authorize endpoint here, and look at this. We have username, password, response type which is equals code, and we have the client ID, redirect URI, scope, and the state. So step 1, the redirect to the Auth server. Look at the URL here. Response type code, client ID, that's the client's registered app ID, redirect URI, where the client wants to be sent back, scope, the permission being requested, and here we have a state which is the random value, and this is exactly the structure I just walked you through. And the step 2, all of these requests are happening on the Auth server's domain. None of them touch the client. They authenticate the user, they handle the approval, the client has no visibility into it. Now if I come right here and go through the callback request here, you will see that this is step 3. The Auth server redirects the browser back to the client, and look at the URL here. There is code parameter and there is a state parameter, the same value the client sent in step 1. The client has to verify these match. If they don't, this callback didn't originate from this user session. And now let me show you something behind the scene. If I open here my terminal and run this command, docker log client app, which is my lab here, and hit enter, you will see that the app is running on the port 3201, and you will see here that the Auth server is basically internal and running in a completely different port. So step 4 here is one that you can't see in your browser side traffic. So because the client's backend is making this request directly to the Auth server to server, your browser isn't involved at all. The client posted the code, the client ID, the redirect URI, and the client secret to the token endpoint. The Auth server returns the access token, the refresh token, and the scope. All of that happened behind the scene between two services completely invisible to the browser. And here, if I go back to my browser, you will see that we have here /userinfo that returned these data. And this is step 6. The client uses the access token to call the Auth server's userinfo endpoint, put your token in the authorization header. And here you can see that the data comes back. Userinfo is rendered. That's the full flow on the wire. 6 steps, every parameter named, every redirect traced, every request explained. The piece I want you to remember from that demo is the back channel exchange in step 4. The one your browser never sees. That single design decision is the reason the authorization code flow is more secure than the older alternative. Think about why. The browser only ever holds the short-lived code. The code is useless without the client secret. The client secret lives on the back end where the attacker can't reach it from the browser. So even if the attacker intercepts the code in transit, even if they exfiltrate it through some flow in the redirect, they can't exchange it for tokens. They need the client secret to do that, and the client secret never leaves the server. This is intentional security design. The flow was deliberately built so that the most sensitive credential never travels through the user's browser. Remember this. We will come back to it when we talk about other flows that don't have this property. Now, I want you to see what this exact button looks like across two real providers, because once you can recognize this on one provider, you can spot the same button and the same bugs on every target you hunt. Right, so here what I have is two buttons. First, sign in with Google and sign in with GitHub. What I'm gonna do is I will click the first button, in that case with Google, and continue all the flow. So I will click sign in with Google, and after this, check my account and continue. And that's it, no more. Now I will get back to my proxy. So here you can see there is accounts.google.com/OAuth/O2/version2/auth. And this is the Google's authorization endpoint. URL looks like this. And the parameters are response type, client ID, redirect URI, scope, state, exactly what I just walked you through. If you can see it, it is here. So here we have http accounts.google.com/o/auth/version2. And after this, we have the response type, the client ID, state, scope, etc. So it is right here. What I'm gonna do is I will get back to my browser again and log out and log in with GitHub. And as you can see, it is loading and I'm logged in. So I will get back to my Kaido here to show you this. So here is the request. Check this out. GitHub authorization endpoint is basically a different host, different URL path, but the same 5 parameters: response type, code, client ID, redirect URI, scope, and state. And look at this. It is the same protocol, the same flow, same parameters. The only thing that changes is the host and the way scope are named. For example, Google uses a URL scope style like this URL. So we have here calendar.read-only, but GitHub uses something like this. For example, email read, okay, or maybe something like repo, and that's it. So it is just different. Google uses a URL style scope and GitHub just uses short names. Surface different. Underneath it is the exact same 6-step dance. Now if I come back right here to my HTTP history and open the callback request for Google, we have here the code and the state. If I go back to the same request for GitHub, you will see that we also have code and the state. Same callback structure, code and state coming back through the redirect on both providers. Once you can read this pattern on one, you can read it on Microsoft, on OAuth 0, on Okta, on every auth provider in the world. They all look like this. That's the authorization code flow, the most common flow on the modern web. 6 steps, same structure on every provider. And like every protocol we have covered, the security of this flow depends on each step being implemented correctly. There are 3 assumptions that have to hold for the flow to be safe. When any one of them breaks, the flow breaks with it. The state parameter has to be validated. If the client just receives the callback and trusts whatever state value comes back without it checking it against what is originally sent, the protection is gone. The whole point of a state is to bend the callback to the original session. An attacker who can initiate a flow with their own account, capture the resulting code, and trick the victim to complete the callback can link the attacker's account to the victim's session, or do the inverse and link the victim's account to the attacker's session. Either direction, you have an account takeover or an account linking attack. The state check is what stops it. Now, the redirect URI has to be matched exactly. If the authorization server allows partial matches, wildcards, or any kind of loose comparison, an attacker can register a malicious redirect URL that passes the check. The code gets sent to the attacker's URL instead of the legitimate one. Code thief, then token thieved. OAuth 2.1 actually mandates exact string matching to close this off, but many existing servers still allow weaker matching for backward compatibility, and that's where bugs hide. The code has to be single use. The first valid exchange should redeem it. Every subsequent exchange should fail. If the OAuth server lists the same code to be redeemed twice, anyone who can capture the code through a refer leak, a server log, or browser history sync has a window to redeem it themselves before the legitimate client does. 3 classic authorization code flow bugs: state not validated, redirect URL not strictly matched, code not invalidated after use. We will exploit each one in a future video. For now, the takeaways is just this: the flow works when every step holds. The flow breaks when any of them doesn't. 6 steps, 6 places where a developer can get something subtly wrong, 6 places to look first when you are hunting on a target that uses OAuth. Remember what made the backend channel exchange secure? The client secret, the thing only the client's backend knows, the thing that proves to the authorization server that this code to token exchange is happening from the legitimate client, not from someone who happened to intercept the code. That works for server-side applications. Calendly has a backend. Their client secret lives in environment variables on their servers, not on any file the user can see. But OAuth isn't only used by server-side applications, it's also used by mobile apps, it's also used by single-page applications. JavaScript has to run it in the browser with no backend involved in the OAuth flow. And for those clients, the client secret model falls apart. Why? Because a mobile app is downloaded onto someone's phone. Anyone who's installed that app can extract the bundle and read the source code. If you put a client secret inside a mobile APK, the first reverse engineer who looks at it already has the key. Same problem for SPAs. The whole point of single-page application is that the code runs in the user's browser. There is no backend layer between the user and the auth flow. So any secret you ship to the browser is by definition visible to anyone who opens the DevTools. The OAuth specification has a name for these 2 types of client. Confidential clients are the ones that can keep a secret, server-side apps. Public clients are the ones that can't. Mobile apps, SPAs, desktop apps that ship with their code visible. The classic authorization code flow doesn't work for public clients. The client secret protection doesn't exist, so an attacker who intercepts the authorization code can exchange it for tokens without needing anything else. And on mobile, intercepting the code is genuinely possible. Here is the attack the protocol designers had in mind. You build a mobile app called, for example, Legit app. You register a custom URI schema with the operating system, something like Legit app/callback, for example. When the OAuth flow completes, the OS knows to send the callback URL to your app. A malicious app on the same device, let's call it malicious app, registers the exact same URI schema. The operating system on the Android specifically has no strict rules about which app actually owns a custom schema. Both apps claim the callback. When the OAuth provider redirects the user back to Legit app/callback where code equals blah blah blah, the operating system might hand the redirect to malicious app instead of the Legit app. Now, the malicious app has the authorization code without PKCE, without a client secret. Malicious app just hits the token endpoint with that code and gets the access token. Game over. So, PKCE was designed specifically to make that attack impossible. The full name is Proof Key for Code Exchange. The idea is to introduce a per-flow secret that the malicious app cannot intercept, no matter how clever they get with the URI schema hijacking. Here is exactly how it works. 7 steps. Step 1. Before the client starts the OAuth flow, it generates a random string, a long one, 43 to 128 characters, cryptographically random. The spec calls this the code_verifier. Step 2. The client hashes the verifier with SHA-256, then base64 URL encodes the result. The output is called the code_challenge. It's a one-way derivation. You can compute the challenge from the verifier, but you can't go backwards. Step 3. The client sends the authorization request like before, but with 2 extra parameters tagged on. The code_challenge equals the hashed value, and the code_challenge method equals S256. S256 stands for SHA-256. Step 4. The authorization server stores the challenge alongside the authorization code it's about to issue. When the user approves, the code gets generated. The server remembers this code was issued with this specific challenge attached. Step 5. The redirect comes back with the code like usual. Step 6. The client makes the token exchange request, but this time, in addition to the code, it includes the original code_verifier, the raw random string from step 1, the thing the attacker has never seen. Step 7. The server takes the verifier, hashes it with SHA-256, base URL encodes the result, and compares it to the stored challenge from step 4. If they match, the exchange succeeds and the token are returned. If they don't match, the exchange is rejected. No token. And that's the old protocol. One random string generated by the client, send it twice, first as hash, then as the original. So why does this stop the malicious app? The malicious app intercepted the authorization code. Great. The code is useless on its own. To exchange it for a token, you need the original code verifier. The verifier is the random string the legitimate app generated before the flow even started in step 1. It has been sitting in the legitimate app's memory the entire time. It was never sent over the wire. It was never in a redirect. It was never anywhere the malicious app could see. So when the malicious app tries to exchange the code, they hit the token endpoint and the server asks for a verifier. They don't have one, or they guess one. The hash doesn't match the stored challenge. The exchange is rejected. The attacker gets nothing. And that's the entire mechanism, as per flow secret that's bound to the code, that never travels publicly, that the attacker can't intercept. Now let me show you what this looks like on the wire. So here I will also log in normally and write my password to complete the flow. Once I'm logged in, I will just switch back to my Kaido, and here I will see the initial request. We have here post to /authorize. Let me make this a little bigger for you. So basically it's the same flow as before. Response type, code, client ID, redirect URI, scope, state, but look at the bottom of the parameter list. Here we have 2 new parameters, this one and this one. So code_challenge, that long base64 254 string, and the code underscore challenge underscore method, which is here, is 256, and that's PKCE. The client just sent the hash verifier to the authorization server. So now if I just continue to see how this works, the next request I will go to the callback, and here you will see that it is the same callback as before, code and state. Nothing to change it there. The PKCE protection lives in the next request, not in the redirect, which is the token exchange. Both to the token endpoint. Look at the body. There is a code, there is the redirect URI, and there is the verifier, the original string, the one that's been sitting in the SPA's memory since before the flow started. Now it's being sent to the OAuth server for verification, and the server takes this verifier, hash it, compares it to the challenge stored in the step 1. If they match, the exchange succeeds, and the token comes back in the response, exactly like here. So you can see here we have the access token and the refresh token. So let me show you something. What I'm gonna do is I will just come back right here to my browser. I will log out, and before I log in, I will just come back right here, intercept the request, and I will come here and log in normally, okay? And once I log in, you will see that the request is intercepted here. What I'm gonna do is just forward this request with no problem, continue, and continue the callback, and continue. And here in this post request, what I'm gonna do is just add one more letter or delete one letter from the code verifier and forward the request. And as you can see here, it is giving me an error. It is invalid because the PKCE verification failed. So the server saw the wrong hash and refused to issue token, even though I had the code, even though everything else in the request was identical. The verifier mismatch killed the exchange, and this is the entire protection. The attacker who has the code but not the verifier gets exactly nothing. So you have seen PKCE on the wire. Verifier generated, client-side, challenge sent in the authorization request, verifier sent in the token exchange, server matches the two and decides whether to issue the token. One thing to flag before we move on, the code challenge method parameter has two valid values. It's 256, which is what I just showed you, and the plain. You should never see plain in production, and here is why. In plain mode, the code challenge is the verifier itself, no hashing. The client sends the random string as the challenge in the authorization request, and the server stores it as is. Then at the token exchange, the client sends the same string again as the verifier, and the server compares them directly. That defeats the entire protection. If the attacker can see the authorization request, they can read the challenge, which in plain mode is the verifier. They now have both behalves of the secrets. PKCE provides no defense against the attacker who can observe the flow at all. Plain exists in the spec for legacy embedded systems that genuinely cannot compute SHA-256. For anything modern, the server should reject any token exchange where the method was plain. If you see a server that accepts plain on top of having no real client authentication, that's PKCE protection being completely defeated. The bigger gap is when the server doesn't enforce PKCE at all. Now imagine a flow where the legitimate client supports PKCE and sends the challenge in the authorization request, but the server doesn't actually require the verifier at the token exchange. It just issues tokens without it checking. An attacker who intercepts the code can exchange it without needing the verifier because the verifier check never runs. PKCE is on the request but isn't on the server, and this is called PKCE downgrade attack. We will exploit it in detail in a future video. For now, the takeaways is just this. PKCE only protects you if the server actually enforces it. If the server treats PKCE as optional, the attacker just sends a request without the verifier and the server hands out tokens anyway. OAuth 2.1, the modernized version of the spec, makes PKCE mandatory for all clients. Public clients have to use it. Confidential clients also have to use it on top of their existing client secret. The reasoning is simple. PKCE costs nothing. It's a pre-flow, it's automatic, it's invisible to the user. So there is no reason to not use it everywhere. In modern Google, GitHub, and Microsoft flows, you will see PKCE parameters even when there is also a client secret behind the scenes. PKCE is now the default. If you intercept on OAuth flow and you don't see code underscore challenge parameter in the authorization request, that itself is interesting. Either the client doesn't support PKCE, which is a sign of an older or weaker implementation, or PKCE is just not being used on this flow, which means whatever protection PKCE would have provided isn't there. So that's PKCE, a bare flow secret that the client generates, sends as hash first and the original second, and the server validates by comparing the V2, designed to stop code interception on mobile, extended to SPAs, now mandatory everywhere. The protection holds if every server treats PKCE as required, not optional. The protection holds if no server accepts plain as valid method. The protection breaks the moment either of those assumptions slips. You just learned the authorization code flow with PKCE, the flow that handles most of the OAuth on the modern web. But OAuth defines another flows too, 4 of them to be exact, each one designed for a different kind of client with different capabilities. You are not going to deep dive every one of these. That's overkill for what hunters need. What you need is recognition, the ability to look at an OAuth flow in your proxy, see which flow it is, and know whether you are looking at something modern, something situational, or something that shouldn't exist at all. Now let's go through them one by one. And the first one is the implicit flow. The implicit flow looks almost identical to the authorization code flow at the start. Same authorization endpoint, same client ID, redirect URI, scope, state parameters. The one difference is in the response underscore type parameter, where the code flow uses response underscore type equal code. The implicit flow uses response underscore type equals token. That single parameter changes everything. And instead of returning an authorization code that gets exchanged at the packet channel for tokens, the authorization servers returns the access token directly in the redirect. No packet channel exchange, no code. The token lands in the user's browser in the URL, and not just anywhere in the URL. The implicit flow returns the token in the URL fragment after the hash, something like https example.com/callback hash access token equals ABC and expires in 3600. The fragment is technically not sent to the server when the browser follows the URL, but that doesn't stop the token from leaking in other way. The browser puts the full URL into history. JavaScript on the page can read it from windows.location.hash. Any browser extension installed has access to the page URL. If the page makes a request that includes a refer header pointing to that URL, depending on the browser's refer policy, parts of the URL can leak in the refer too. The implicit flow designed for SPAs back when PKCE didn't exist. Now that PKCE exists, the implicit flow officially deprecated. OAuth 2.1 removes it from the specification entirely, but you will still see it. All the apps, legacy integrations, providers that haven't updated their SDKs. If you see response underscore type parameter equals token in the authorization request, that's a sign of an older implementation, and the token in fragment design is its own attack surface. So treat that as red flag worth investigating. Now, quick recognition. Implicit flow showed up as response underscore type parameter equal token in the authorization request. The callback URL has parameters after the hash, not after a question mark. There are no token exchange post anywhere in the flow. Second flow is client credentials. This one's different from everything else we have covered because there is no user involved at all. Client credentials is for machine-to-machine communication, one backend service talking to another. No browser, no constant screen, no human in the loop. This flow is only one request. The client takes its client ID and its client secret, posts them directly to the authorization server tokens endpoint with grant type equal client underscore credentials, and the server returns an access token. That's the whole flow. No redirect, no /authorize, just /token. So why does this exist? Because applications talk to each other constantly. A CI pineapple needs to pull artifacts from a private repo, a backend microservices that needs to call another microservices API, a cron job that hits a third-party data provider every hour. They just need to authenticate as themselves as an applications and get an access token. And there is no refresh token in this flow. There is no user session to maintain. When the access token expires, the service just does the old flow again and gets a new one. For hunters, client credentials is mostly invisible from the user side. But if you ever came across leaked client credential, for example in a public GitHub repo, in a mobile APK that was supposed to be confidential client, in a configuration file accidentally exposed, those credentials let you mint tokens for that service directly. That's a real bug class. It happens more than people admit. So quick recognition, the post request to /token endpoint with the grant type equal client underscore credential. Here, there is no user facing redirect step and no refresh token in the response. The third flow is the device authorization flow. Have you ever signed into YouTube on a smart TV or used GitHub CLI tool? When you do that, the TV or the CLI tool can't host a browser flow. There are no full keyboards. There are no good way to type in a URL and a password on a TV remote. The device that you can't run a browser delegates the auth step in a device that can. Here is how it works. The TV asks the authorization server for a flow start. The server returns two things: a short user code and a verification URL like youtube.com/activate. The TV displays both on its screen. You take out your phone or your laptop, you go to the verification URL, you enter the short code, and you authenticate normally and approve. Meanwhile, the TV is polling every few seconds. It hits the authentication server's tokens endpoint with this, and at the end, you can see the device code it was issued at the start. Most of those polls come back with a pending response. The user hasn't approved yet. The TV waits and it tries again. When you finally approve on your phone, the next poll succeeds. The TV gets the access token and the refresh token. From that point on, your TV is signed in. And here is a quick recognition for this button. You will see a short human readable code displayed on the device and a separate URL like domain.com/activate or domain.com/device. You will also see a post request polling button to the token endpoint on fixed interval. You will also see it in the TV apps, CLI tools, smart speakers, anything with limited input. The device flow has its own bug classes. Phishing attacks, where an attacker tricks the victim into typing the attacker's device code into their own browser, effectively linking the attacker's device to the victim's account. Also, race conditions on the polling, brute forcing against the short user code when rate limiting is weak, but the core mechanism is legitimate and necessary for the limited input devices. Now, the fourth flow is ROPC, Resource Owner Password Credential, I think. This is the flow that shouldn't exist anymore. In ROPC, the client app collects the user's actual username and password, not through OAuth, not through a consent page. The user just types their credential into a form in the client app. Then the client posts those credentials directly to the auth server's token endpoint with grant type equal password, the username and the password. The auth server validates the password and returns an access token. Let that sink in. The client app has the user's password. So, do you remember the entire point of OAuth? It was designed to make the password anti-pattern go away, to stop third parties from reading your password, to put the auth flow in the provider's domain so your credentials never hit the client. ROPC undoes all of that. The user types their password into the client. The client now sees your password. If the client is compromised, the password leaks. If the client stores it for remember me, the password is safe in their databases, and there is no MFA prompt because the client controls the form. There is no consent screen because there is nothing to consent to. There is no scope choice because the user can see what's being requested. It's just a password being passed through. ROPC was originally included in OAuth 2.0 for one specific case, helping organizations migrate from legacy non-OAuth systems where users were already trained to enter their credentials directly. Even then, it was discouraged. Now it's officially deprecated in OAuth 2.0 best practices guide and completely removed on OAuth 2.1. And here is a quick recognition for it. If you see a post request to /token with grant type equal password, username and password fields in the request body, no /authorize step, the client app has a login form that asks for OAuth provider's credentials. If you see this on a target, that's a finding by itself. It is a misuse of the protocol that breaks every guarantee OAuth was designed to provide. Okay, so those are the four other flows: implicit, client credential, device, and ROPC. You don't need to know how to exploit each one from memory. You just need to recognize them when you see them and know which one are modern, which one are situational, and which one shouldn't exist. OAuth 2.1 is what happens when a decade of bug bounty reports, security researchers, and bad implementations gets fed back into the specification. The OAuth working group looked at OAuth 2.0, looked at every way developers had had gotten it wrong over 15 years and wrote a new spec that bakes the best practices directly into the protocol. So here is why it changed. Number one, PKCE is now mandatory for every client. Public clients have to use it. Confidential clients have to use it too, even when they also have a client secret. This closes off the entire family of code interception attacks across every flow that uses authorization codes. Number two, the implicit flow is removed completely. It's not a valid grant anymore in OAuth 2.1. If you see a server that supports it, the server is following OAuth 2.0, not 2.1, and that's a sign of an older implementation. Number three, ROBC is removed. Same as implicit, not a valid grant type. If a server still supports grant_type equal password, it hasn't moved to 2.1. Number four, refresh token rotation is required for public clients. The reuse detection model we covered is now mandatory, not optional for anyone running SPA or mobile app. Number five, barrier tokens cannot be passed in the URL query strings. They have to go in the authorization header. This stops token from leaking into the logs, refer headers, and the browsing history. Number six, the redirect URI has to be exact string match against what the client registered. No more prefix matching, no more wildcards, no more post reversal check. The full URL has to match character for character. This is the most important hardening change because redirect URI matching bugs were the source of countless real-world OAuth account takeovers. And that's OAuth 2.1. PKCE everywhere, implicit gone, ROBC gone, refresh rotation enforced, no barrier tokens in URLs, exact redirect URI matching. For hunters, this is your safety baseline. Anything you find in the wild that violates one of these rules is potentially reportable. A server still accepts implicit flows, a server allowing wildcard redirect URI, a server taking barrier token in the query string. Every one of those is a sign of an older or weaker implementation. And every one of those is the kind of gap that real account takeovers have been built on. So that's the rest of the OAuth flow landscape. 4 flows you need to recognize. One modernized spec that looks down the rules, and one constant theme. The protocol gives you the tools, and the protection only holds if the server enforces them. OAuth answers one question: what is this app allowed to do with the user's data? That's authorization, permissions, access. OAuth doesn't answer the other question: who's this user? That seems like a strange omission. Every sign in with Google button feels like authentication. The user shows up, the app knows who they are, and job done. But that's not what OAuth does. OAuth gives the app permission to call Google's API on the user's behalf. The app can then call Google's user info endpoint and ask, tell me about the user who authorized this token. But there is a workaround. OAuth itself never carried the user identity. Apps would hack an identity on top of an authorization protocol because there was no standard for that real thing. Until 2014, that's when a new specification got published on top of OAuth. It added the missing identity layer. It standardized how the user's identity is proved, what format the proof takes, and how the client should validate it. The specification is OpenID Connect, OIDC. OIDC is not a replacement for OAuth. It's a layer on top. Every OIDC flow is an OAuth flow underneath. Same redirects, same code exchange, same access token. OIDC just adds one more thing alongside the access token, a new kind of token, the ID token. This is the distinction you have to internalize. The access token says this app has permission to do S. It's a key to an API. The ID token says this user is who they say they are. It's a statement of identity. Different token, different purpose, different audience, different ways of being validated. So how do you turn an OAuth flow into an OIDC flow? You just add one scope, which is OpenID. When the client requests scope OpenID alongside with the other scopes, the authorization servers knows to treat this as OIDC flow. Alongside the access token, it returns an ID token. The full request usually looks like scope equal OpenID email profile and asking for identity plus the user's email plus their profile claims. The ID token is always a JWT, signed, verifiable with a standardized payload to contain the user's identity claims. Now let me show you what one actually looks like. Here what I'm gonna do is just log in normally, to capture the data on my Kaido. And if I get back to my proxy here, you will see there is post request to /token, but here we have something different. We have here the access token and the ID token. What I'm gonna do is copy this cool ID token and go to JWT analyzer and paste it here. So check this out. The ID token is returned alongside the access token with the OAuth token change. It is a JWT, same 3 bars you already know, header, payload, signature. And check this out in the payload. Look at the claims here. This is what makes it an ID token instead of just any JWT. Standardized claims that says who the user is. So for example, here we have IIS, which is the issuer. So the OB, the OpenID provider. For this lab, it is just my domain. On real targets like Google, it would be something like https://accounts.google.com. Either way, this tells the app which provider minted this token. The app has to verify that this matches the provider expected, or it could be accepting a token from a completely different issuer. And as you can see, there is the sub, which is basically the subject, and this is the permanent unique identifier for the user. Within this issuer, it doesn't change. It's not the email, it's not the username. And here in the lab, it's auth 0 and 1 2 3 4 5. On Google, it's a stable OBQ string. And after this, we have the AUD, which is basically the audience, and this is the client ID of the app. This token was minted for. Here it is client_OIDC. So the app has to verify this matches its own client ID. If it doesn't, this token wasn't issued for this app. It might have been issued for a different app and somehow ended up here. And this is the token confusion attack. After this, we have the EXP and IAT. And basically, this is expiration and issued at timestamps. Basically, they are standard JWT claims. The app has to check the token hasn't expired. And as you can see here, we also have another claim called email. And email is just the user's email address, but more importantly, we have email_verified. Email verified, it is a boolean. This is the most under-checked claim in the OIDC. It tells you whether the provider has confirmed this user actually owns this email address. And we will come back to that in a second. We also still have the name, which is basically the profile claim. Name in the lab is just Alice. On real provider, you will also see picture, local, and other. This kind of thing you would populate a user profile from. And the signature is basically same as any JWT. So the app is supposed to fetch the provider's public keys from the JWKS endpoint, verify the signature, and only then trusts any of the claims inside. So in this example, what I'm gonna try is just go to the HTTP history, send this to reply, or maybe let me get a GET request, and here I will change this endpoint to be the JWKS endpoint, and I will just send the request. And here you will see that we have the key, and this is the public key that I can use to verify that this token is valid, but I can't issue a new token with it. So that's the ID token. A JWT contains the user identity claims signed by the OB intended for the client to validate. Now, let me walk you through how this fits together in real sign-in with Google Flow end to end. The user clicks the button. The client redirects to Google Authorization Endpoint. The request looks like just the code flow you saw before, with 3 additional pieces. First one is the scope, includes OpenID, and then the request includes balance and a random value the client generates that will be echoed back in the ID token as replayed protection. And the request uses PKCE because every modern OAuth flow uses PKCE. The user authenticates at Google. The user approves the consent screen, which lists the scopes including OIDC standard ones like email and profile. Google redirects back to the client with the authorization code. Then the client makes the token exchange, both to Google's token endpoint with the code, the PKCE verifier, and the client secret if it's a confidential client. Google's response contains 3 or 4 things. The access token, which is valid for calling Google API. The refresh token, if requested. The ID token, this is newly minted JWT, contains the user identity. And the expires in for the access token. Now, the client has to validate the ID token before it does anything with it. This is where most OIDC implementation bugs live. The client checks the signature signature. It uses Google's public keys fetched from Google's JWTs endpoint. The endpoint URL is discovered through Google's well-known configuration at accounts.google.com/.wellknown/OpenID configuration. The client checks ISS, which is the issuer, making sure to match the HTTPS accounts.google.com. The client checks the AQD, matches its own client ID, and the client checks EXP in the future. The client checks nuance, making sure it matches the value it sent in the authorization request as well. Only after all of that passes, the client trusts the claims inside it. Then the client uses the validate claims to identify the user. The subclaim becomes the user's permanent identifier in the app's user database. The email is stored for display purposes, the name and picture populated in the UI, and so on. The access token is set aside for the resource server. If the app wants to call Google Calendar later, it uses the access token. The access token never carries the identity. The ID token never accesses resources. They are separate tools for separate jobs. Now I told you we would come back to email_verified parameter. This is the gap I want to plant in your head. A lot of apps treat OIDC the same way they treat their own login system. They store users by email. When someone signs in through OIDC, the app looks at the email claim in the ID token, finds it matching the user record, and signs them in. The problem is that the email is just a profile attribute. It can change. It can be claimed by anyone, and critically, the OIDC provider may have never verified that the user actually owns that email. So picture this scenario. Attacker creates an account on an OIDC provider that doesn't verify the email ownership. They put the victim's email address into their profile. The OIDC provider issues an ID token with the email, for example, victim@target.com, and email_verified parameter equal false. The attacker signs into the target app using OIDC. The target app looks at the email, finds the victim existing account, and treats this OIDC session as the victim's, which is basically account takeover. And the fix is to basically use sub plus ISS together as the user's identity, not email. Email is profile attribute that can change. ISS plus sub is a permanent unique identifier scoped to the provider. If the app must link OIDC users to existing accounts by email, at minimum, it has to check that email_verified parameter equal true before trusting the email. If the app doesn't check email_verified parameter, the email claim is worthless from security standpoint. And this is the most common SSO misconfiguration in the wild. We will explore a specific variation of it in future videos. For now, just hold this. The email claim is a string. It only carries security weight when email verified is also true. And the only identifier you should actually trust as identity is sub scoped to the issuer. Before we move on, one more comparison you need to know. OIDC is the modern protocol for federated identity on the consumer web. Sign in with Google, sign in with Apple, sign in with Microsoft, all basically are OIDC. But OIDC has a cousin, an older protocol that solves the same problem differently and still dominates the enterprise world. SAML, Security Assertion Markup Language, created in early 20s, current version is 2.0 from 2005. It's XML based. The identity proof isn't a JWT. It is an XML document called SAML assertion. The signature isn't a JWT signature. It is an XML signature. The flow isn't a series of HTTP redirects with JSON. It's often a form of post that auto-submits an XML response. SAML dominates enterprise SSO. If your company uses Okta, Microsoft Entra, OneLogin, or Ping Identity to log into Salesforce, Workday, or ServiceNow, that's almost certainly SAML happening under the hood. You can spot SAML in your proxy in seconds. You will see big XML blobs, often base64 encoded, and form fields named SAML request or SAML response. The endpoints will have names like /SAML/SSO or /SAML/ACS or /SAML/login. There is no JWT, there is no /token endpoint, there is no /authorized redirect with the 5 parameters. It is completely different protocol with a completely different shape. The bug classes here are different too. OIDC bugs live in the JWT validation, audience confusion, nouns reuse, and the claim trust. SAML bugs lives in the XML signature wrapping, XML external entity injection, audience confusion, and reply attacks on the assertion. You don't need to know how to exploit SAML in this video. You just need to know which one you are looking at when it shows up in your traffic. JWT and JSON and ID_token, that's OIDC. XML form auto submits and SAML response, that's basically SAML. So that's OpenID Connect. OAuth tells the app what it can do. OIDC tells the app who the user is. Different tokens, different validation, different bug classes. And the most important claim in the entire spec is the one most apps forget to check: email verified parameter. Keep that one in your head. Up to this point, every section taught you how a piece of the OAuth stack works when it's implemented correctly. This section is different. This section is the shift in how you look at OAuth flows from now on, the shift from reading the protocol to reading the implementation, from seeing the design to seeing the gaps. Here is the mental model. Every protection in OAuth stack exists for a specific reason. Someone somewhere broke a real system and a protection got added to the spec to close that gap. So if you can answer two questions about every protection, you have stopped reading OAuth flows and starting hunting them. Question 1 is, what attack does this protection prevent? And the question 2 is, what happens if this protection isn't there? If you can answer both questions for every protection in the stack, you have inverted the problem. You are no longer trying to spot bugs by trial and errors. You are scanning for absences. You are looking at an OAuth flow and noticing the protection that should be there but isn't. And the moment you spot one, you already know what attack it enables. And that's how best OAuth hunters work, not by memorizing payloads, but by holding the protection map in their head and reading flows for missing pieces. Now, let me walk you through that map. Starting with sessions, the HTTP only cookie flag blocks JavaScript from reading the cookie. If it's missing, every XSS on that domain becomes session thieved. The attacker writes document.cookie, exfiltrates the session ID, and replays it at the user. The flag turns every XSS into an account takeover. Missing a flag, every XSS becomes critical. The same site cookie flag blocks cross-site requests from carrying the cookie. If it's missing, the site is vulnerable to CSRF. An attacker's site fires a request to the target. The browser attaches the session cookies automatically, and the target server treats it as a legitimate user action. Missing a flag, every state-changing endpoint that doesn't have its own CSRF token is exposed. Now, let's move to JWTs. Signature verification proves that the token wasn't tampered with. If the server doesn't actually verify the signature, or if it trusts the algorithm declared in the header without checking against an allow list, the attacker can rewrite the payload to whatever they want: rules, identifiers, and scopes. Missing or broken verification, the entire JWT is just a base64 string the attacker controls. Now, let's talk about OAuth. The state parameter pins the authorization callback to the user's original session. If the client doesn't validate the state, an attacker can initiate their own OAuth flow, capture the resulting code, and trick the victim into completing the callback. Either directions the linking goes, you have an account takeover. Missing a state validation, the protocol is open to OAuth CSRF, account syncing attacks, and the pre-authorization hijacks. Exact redirect URI matching ensures that the authorization server only sends codes to URLs the client legitimately owns. If the matching is loose, if there is a wildcard or prefix checks or bus traversal tricks, an attacker registers a malicious redirect URL that passes the check and intercepts the code. Missing exact matches, codes get stolen, tokens get stolen, accounts gets taken over. PKCE binds the code exchange to a bare flow secret the attacker cannot see. If the server doesn't enforce PKCE or accepts the plain method as fallback, the protection collapses. An attacker who intercepts the code exchanges it without needing the verifier. Missing PKCE enforcement, code interception attacks comes back from dead. Now, the packet channel exchange keeps the token of the browser entirely. If a flow returns tokens through the browser instead of through server-to-server exchange, those tokens land in the browser history, in a refer header, and in a JavaScript that runs on the page. Missing packet channel exchange, tokens leak through the user's own browsing footprint. The client secret proves that the application requesting a token exchange is the legitimate client, if a confidential client secret leak, or if a public client somehow has one bundled into a binary or JavaScript file, an attacker can mint tokens as that application. Missing or expose the client secret, the application's identity is no longer a guarantee. Short-lived access tokens limit the damage window when something does leak. If a token lasts an hour, a thief has at most an hour to be exploited before the token dies. If a token lasts a year, the same thief is a year-long compromise. Missing short-lived design, a single leak becomes a long-term backdoor. Refresh token rotation turns the long-lived refresh token from a backdoor into a tripwire. Single-use tokens invalidates on use, with reuse detection that revokes the entire family when thief is detected. If the server skips rotation or doesn't detect reuse, the stolen refresh token works for the full time of the original authorization. Missing rotation thief becomes invisible and indefinite. Scope enforcement keeps token limited to what the user actually guaranteed. The token says calendar read. The resource server has to check that on every single API call. If it doesn't, the token becomes a generic access pass and the user's honest decision becomes irrelevant. Missing server-side scope check, every token is effectively a full access token. And that's the table. 11 protections, 11 bug classes when the protection is missing. If you are new to OAuth, this list looks like a checklist of things to learn. If you have been doing this long enough, this list is exactly how you hunt. You intercept a flow, you start scanning for protections. Check PKCE, check state, check exact redirect URI match, check same site, check HTTP only, check signature verification. You have to test this one explicitly, but you know how to test it. Refresh rotation, you watch it for across a refresh cycle. Scope enforcement, you probe it by calling endpoints with mismatched scopes. Every check passes, the flow is solid, but the moment a check fails, you don't ask what kind of bug this might be, you already know. You read the gap and immediately match it to its bug class because the table is in your head. And that's the shift. Regarding protocol becomes regarding the implementation. The protocol tells you what should be there, the implementation tells you what actually in. The gap between the two is the bug. We have covered the full protection map now. Every row I just walked you through, you can recite the attack it blocks and what happens when it's missing. That's the lens you carry into every auth flow you ever touch. And that lens is what makes the next video is possible. In a future video, we are going to take this exact table and walk through real exploitations for each one. Real CSRF on missing state, real code theft on weak redirect URI matching, real signature bypass on JWT migration, real SSO takeover on missing email verified parameter, real PKCE downgrade, real session hijack on missing HTTP only. Every row a working exploit. The reason that this video is going to make sense to you is because of this one. You can't break what you don't understand. You can't spot a missing protection if you don't know what the protection does. You can't recognize a bug class if you have never seen the design it violates. Now you have all of it. 11 protections, 11 bug classes, one way of reading every auth flow you will ever see. That's auth. Not all of it, there is always more, but everything you need to read any flow on any target. You came into this video knowing what state and code challenge and redirect URI looks like in a request. You are walking out knowing why each one exists, what each one protects, and what happens when each one is missing. You came in seeing sessions and JWTs as two different things. Now you can explain why they exist for the same reason. Stateful versus stateless, DB lookup versus signed tokens. The session is a record on the server. The JWT is a record in your hand. You came in confusing OAuth with authentication. Now you know OAuth is permission and OIDC is identity. The access token is for the API. The ID token is for the app. Different jobs, different validations, different bug classes. You learn to read the 6 steps authorization code flow. You learned why the packet channel exchange exists. You learned PKCE and why it's now mandatory. You learned the 4 other different flows and which one shouldn't exist anymore. You learned OAuth 2.1 and which protections it looks in by default. And then we put all together the security design table. Living protection paired with the bug classes that appear when they are missing. the lens you carry into every auth flow from this point on. If you got through this video, you can do something most hunters can't. You can open an OAuth flow on your proxy, read every parameter, name every protection, and immediately see what's there and what's not. That's the skill. The only thing left is putting it all to work on real target. I told you at the start I wasn't going to break any of these flows in this video. That holds. Breaking is a video of its own. Every row of that table is a real bug class, real exploit, real account takeovers, real session hijacks, real signature bypass, real SSO failure. All of it with working exploitations. But here's the thing. I'm already cooking part 2. Every row in the table I just walked you through, exploited live. Each protection turned into a real attack that live when it's missing. So if you want it faster, drop part 2 in the comments. The more of you ask, the sooner I push it. And if you found this video helpful, do not forget to like, subscribe, and hit that bell icon for more cybersecurity content. And if you have any questions, feel free to drop them in the comments below, or you can reach me directly on X. Until next time, stay curious and stay secure.